All right, so when we look at those redox reactions, when we have them occur spontaneously, um, energy is just going to, or electrons, excuse me, are going to be transferred essentially automatically, and we're going to see energy is going to be released in that process. So actually, if we go back for a second here, the reaction we're looking at, so we've got solid zinc in a copper solution, so we've got the copper 2 ions here. And what we're going to see in this case is the zinc and the copper are essentially going to switch places. So we're going to see the zinc's going to wind up in solution. That's why we lose a little bit of that blue color. We're replacing the blue copper with the colorless zinc. And then you can see that new solid is forming on the zinc. That's actually going to be the copper solid itself. And with these spontaneous ones, we're going to refer to these as voltaic cells. And essentially, if we kind of just hook them up in a certain way, we can allow those electrons to travel through a wire and essentially just kind of create a little battery. And when we have these, we've got a couple different pieces. So one, or the two big ones are going to be the anode and the cathode. And the way the chemistry sort of saying for those is anox and then red cat. Not the best sayings, but just so you can kind of remember what's going to be happening there. And what that stands for is anode oxidation. So at the anode, we're going to see the oxidation process occur. So that's why if we look at the picture here, we're thinking about that reaction. We've got solid zinc, but then it's getting converted into the +2 ion. So it's being oxidized because it's losing those 2 electrons. And then at the cathode, it's going to be the other electrode. We're going to see the reduction piece of red cat, reduction cathode. So that's why in this case, we're seeing the copper 2 ion is taking those 2 electrons and forming more of the solid there. But with this, we also need the sort of little tube here. It doesn't always have to actually be a tube like we see here. But this is going to be what's known as the salt bridge. And the reason we need that is because once we have a single electron move, so once we have zinc give up an electron and it makes it to the cathode, then we're going to have an imbalance of charge. So that we'd actually just see the flow of electrons would just cease to occur, or to continue at least. So what we have is the salt bridge here, and you can kind of see we've got nitrate ions, we've got positive sodium ions, and what those are going to allow us to do is just keep the charge balance between these two different beakers, between these two different electrodes. If you think about it, with the negative electron moving towards the cathode, that's why we've got sodium ions moving there. So we've got to balance out that negative. And then with the anode, they're losing that electron. So now we have the negative anion, something like nitrate, moving that direction again, just to keep the balance of the charge between these two different solutions. So if we look here, we've got a whole bunch of writing, but essentially it's just showing us an oxidation reduction reaction. And this one's already balanced, so we don't really need to go through and look to see how many hydrogens we need to add or what or anything like that. We've already got the balanced redox reaction. And what it's going to be is taking the dichromate ion in an acidic solution along with iodide. And then we're going to be producing just the chromium 3 ion, solid iodide, and liquid water. And the reaction is going to be spontaneous, and we can set it up with a beaker of potassium dichromate in sulfuric acid. So that's going to be where we get the dichromate from, as well as the hydrogen from for the acidic piece of this. And then the potassium iodide is just going to be in the other beaker. We'll have a salt bridge connecting those two. So if we go back, we can kind of just think of one of these beakers is going to have the dichromate and the acid. Another one's going to have the iodide, and then we'll have a salt bridge just connecting them. And then we'll have a metallic conductor in each of those solutions. So that's just going to be the electrode, that metal piece that's going to be connected with a wire, allow the flow of electrons between those two solutions. And then we're going to see an electric current is going to be generated again, because this will be a spontaneous process, the way this reaction is set up. So what we want to do is use this information to determine what reaction is going to be occurring at the anode, what reaction is going to be occurring at the cathode, where the electron is going to be moving from. With the salt bridge, we want to think about, we don't know in this case specifically what, or actually we'd have the potassium and the sulfate ions. So we could think about which direction each of those ions would move as the electrons flow. And then finally, we want to think about the signs on those electrodes. So if you want to take a moment, look at this reaction, and then kind of look at the oxidation numbers, see which is changing, so we can identify which is being oxidized, which is being reduced. And then we can remember anox and red cats will have the oxidation occurring at the anode, the reduction piece occurring at the cathode. And then we can use that to determine which direction the electrons are flowing from which solution to which, as well as just the other little piece of information here. Okay. But if we look at it, oops, I should have put the reaction here, I guess. But if we look at the chromium to start, we've got it with 7 oxygens, so that's going to be a negative 14 from all of the oxygens. But we've only got to balance out 12 of them because we're going to have a negative 2 charge. So 12 divided by 2 is just going to mean we're going to have chromium with a positive 6 initially. But it's going to be a plus 3 on the right-hand side, so we're going to see that the chromium's getting reduced. And then if we also look at the iodine, it's going from negative 1 to 0 as a neutral compound, so the iodide is going to be getting oxidized. So when we look at each of these reactions, the iodide is oxidized, so anox, we're going to see the iodide will be at the anode, which means the chromium is going to be at the cathode. And if we look at these reactions, so these are the half reactions, we don't have them balanced for charge, so we've also just got to make sure to include with the half reactions those electrons, because now we've got 6 iodides on both sides, as well as a negative 6 charge overall. And then similarly up here, now we've got 14 hydrogens, 2 chromiums, 7 oxygens, and then is that going to be plus 6 charge on each side? Yeah. So when we think about the other pieces of this question, so again, the chromium is going to be at the cathode because it's getting reduced. The iodide half reaction is going to be at the anode because it's getting oxidized. Direction of the electron migration then, so it's going to be going from the anode to the cathode because the anode's where it's releasing those electrons. The cathode's going to be the substance that's getting reduced, that's gaining them. So in this case, we would see them go from iodide here to the chromium, or the dichromate, I guess, over here, really. And then what else do we have to do? Reaction at the cathode, direction of and then we want to think about the direction of the ions. So we're going to have this salt bridge. And if we think about it, we had potassium dichromate and then sulfuric acid. So we've also got sulfate ions here. We've also got potassium ions here. So what we're going to see is on the anode, the one that's giving up those electrons, so the iodide, it's going to form solid iodine here. But what's going to happen is it's losing those electrons. So we're going to see the sulfate ions are going to move towards the anode to keep that balanced charge, which means the potassium ions are going to move towards the cathode because now we have the negative electron moving in that direction. So we've got to balance out that negative with a positive. Whereas at the anode, we're losing a negative, so we've got to kind of replace it there. And then with the final piece, you can already kind of see it here. We've got the anode is going to be considered negative. The cathode going to be positive, and it kind of makes sense if you think about it. Opposite charges are going to repel, so we're going to sort of push the electron away from the anode. It's going to be attracted to that cathode. And this is going to be a pretty standard kind of concept with a whole bunch of different voltaic cells. The only thing that's going to be different is specifically what those substances are. So it's not always going to be iodide and dichromate and chromium. We're not always going to have 6 electrons involved. It's not always going to be potassium and sulfate, but the general idea with the movement of those electrons, the oxidation occurring at the anode, the reduction occurring at the cathode, the movement of the anions and cations, things like that are going to be the same. So if we look at the Voltaic cell, excuse me, we can look at each of those sort of pieces first. And then, like I mentioned before, it doesn't always have to be a salt bridge. So in this case, it's kind of just one container, but it's being split by a porous barrier. So that's going to allow ions to move through in a similar way as the salt bridge, just kind of a different setup. I think some cases people even just use kind of like a sponge almost to keep them apart, act as the salt bridge there. But with these voltaic cells, we can look at the anode and the cathode kind of individually. And what's happening is at the anode where we have that oxidation, it's losing the electrons. So we're seeing them transfer to the cathode there. So that's why if you look at the picture here, we've got the zinc solid initially, but then it's losing those electrons, so it's going to dissolve into solution. That's why we wind up with the Zn2 plus aqueous. And then just the reverse would be happening at the cathode. It's going to be gaining 2 electrons. So we're going to see the copper ions are then going to start to plate that electrode. Saying that same thing. So again, with it, that's why if we had this reaction occurring, you would start to see the blue color from that copper solution start to fade. And if you take in certain chemistry courses with me, you may have seen similar reactions there where we actually had that copper and zinc switch place. But we're just going to see that blue color fade because we're going to be taking those aqueous ions that are giving us that blue color and just have them converted into the solid. That's going to then plate the cathode itself. And then with this general process, what we're going to see similar to a waterfall is the movement of these electrons is only going to be spontaneous in one direction. So the reason we can kind of think of it as a waterfall is because the water here is only going to move from the top of the waterfall down to the rest of the water there. Similar to the electrons, they're just going to flow spontaneously from anode to cathode. If we wanted to have them go in the opposite direction, we would have to input some amount of energy. And then the potential difference is going to be how we kind of quantify these. And this is going to help us actually determine if a certain setup would be spontaneous or not. So we can't just take any substances we want and kind of hook them up in that voltaic cell setup. We've got to be selective about which we have, and then we're only going to see it move in one direction. Where we're going to have what's known as the electromotive force, or more commonly, just the cell potential. And that's just going to tell us the difference in the potential energy essentially between those anodes and cathodes. But with this, typically we're going to have the unit volt here. And then with the volt, just recognize that it's going to be equal to a joule per coulomb. And then with a coulomb, I forget exactly what it is. But I think an electron is like 10 to, here it is, yeah, 1.6 times 10 to the negative 19th. So an electron, the negative charge associated with that, is going to be much, much smaller than even just a single coulomb. But with these reduction potentials, these cell potentials, we're always going to kind of write them in terms of reduction. So we could have the opposite occurring if you think about taking any of these reactions. We could switch the arrow to the other direction. In that case, it would just be oxidation. But with these potentials, we're always going to write them in terms of the reduction reaction. And what we're going to have them sort of based on is just a standard. And that standard is just going to be known as the standard hydrogen electrode. And that's why if you look at this table here, you can see a whole bunch of different reduction half reactions. So like fluorine gains 2 electrons, goes from 0 to -1. Lithium all the way at the other end of the spectrum, +1, gains an electron, becomes 0. So all of these are shown reduction. But we can look at the potential. And they're just going to be based on the hydrogen electrode. So they're just going to be, that's where we're going to consider the hydrogen electrode to be the reference. And the way this is set up, you can kind of see here is we've got a platinum wire that can basically act as the anode or the cathode, the way we have it set up. But we're just going to take hydrogen, combine it with 2 electrons to give us hydrogen gas, or take the hydrogen ions, I should say. And we're just going to, by definition, sort of set this at 0 volts. So this is just going to be the standard. If it's got higher potential, we'll see a positive number there. So stuff like the fluorine. Stuff that's going to be spontaneous, we'll see is going to be positive when we look at both halves combined. So we won't just be looking at reduction. We'll also need to examine the oxidation piece. But the values in this table are just going to be in comparison to that standard hydrogen electrode itself. And then when we're looking at a cell, like I just mentioned, we've got to consider reduction and oxidation. So we're going to have both of those pieces occurring. So if we're looking at a cell, we can look at both of those pieces and kind of just use the reduction potential for each of those half reactions. And what we're going to do there is you can kind of see we've got 2 very similar equations. With the top one here, this is going to be taking the reduction potential at the cathode minus the reduction potential at the anode. So in both cases, we're thinking about the actual reduction half reactions here. So we would be able to just take the values directly from a table like this and plug them in. But with the second version of this equation, essentially the same thing. So we're still looking at the standard potential of the cell as a whole. So we're thinking about a voltaic cell or flow of the electrons there. The first piece with the cathode, remember red cat, that's what we're actually going to see there. We're going to see reduction at that cathode. So we can just take that reduction half potential, or reduction potential for the half reaction, I should say, and plug it in. But then with the other electrode, the anode, we're going to have oxidation there. So if we want to look at the oxidation half reaction, we're just essentially going to flip those reactions, which is going to flip the sign on the cell potential. And that's why the difference between these two right here is just the negative minus, or negative and the plus sign. It's just kind of determining, or based on whether we're focused on the anode in terms of the reduction half reaction, or if we're actually thinking of it in terms of the oxidation half reaction. But the magnitude of that number is going to be the same. It's just with the opposite direction, we change the sign. I, for the most part, use it like this, just so you can always have cathode minus anode. You don't have to worry about converting the number at all in terms of flipping the sign. But if it makes more sense for you, you can always take those reduction potentials, and then for the oxidation one at the anode, you can always just flip the sign. But I usually just do the negative, but it'll be the same point. So if we look at the reaction here, we've got zinc and then copper. So with the zinc, that's going to be where we have the oxidation taking place. And with this, if we wrote the reduction half reaction for zinc, you can see negative 0.76, because in this case, it's zinc 2 plus gaining 2 electrons, going to the solid zinc. So we can use that value just like that. Or if we want to think about it in terms of the oxidation half reaction, excuse me, we would just flip the sign on it, make it positive 0.76. But again, it's representing essentially the exact same thing. It's actually representing exactly the same thing. And then for the reduction half reaction, the potential there, positive 0.34. So in this case, we're looking at just this reaction exactly. So if we went back to that table again, we wouldn't have to change anything about it, because in this case, it's the exact same reaction here. Whereas the previous one, we had the reverse. That's why we could flip the sign if we wanted to, or we could just do minus the negative number. But if we want to get the cell potential for this entire voltaic cell, what we're going to do is just think about the cathode minus the anode, or cathode plus the oxidation potential at the anode. And either way, we're going to get the same number. So again, I usually do it like at the top here, so we can always just have minus whatever that number is. Get 1.10 volts, excuse me. But with the bottom one here, again, same exact thing. It's just in this case, we have plus because we're looking at it from the oxidation perspective. And that's why we've also flipped the sign here. Yeah, ultimately get to the exact same point. So however you want to do it, but I typically have the other example. And then with this, just to kind of look at the same reaction from a different perspective. If we were given this reaction and we were given the cell potential, and then just note with the little bubble here that just stands for standard conditions. So we're just going to have concentrations of 1 for everything. Solids don't affect it at all, so that's why we don't care about the concentrations there. But we were given the cell potential, and then we were given the reduction potential for zinc. We want to calculate the reduction potential for the reduction of copper. So what we would do in this case is kind of just think about this equation. In this case, we would have the E cell value. We would have the reduction at the anode. So we could just plug those values in, and in this case, just solve for the cathode there. So with this next question here, this sample exercise 20.5, it's that same reaction. It's just kind of looking at it from a different perspective. And then with it, I didn't put the cell diagram because it's just going to be the same one we see here. So with this equation, just like any equation, if we've got all of the variables but one, we can always solve for that one, solve for what that is. It's just depending on if we're looking for the cell potential overall, like we did initially here, or with the next one. If we know the overall cell potential and we know one of the half reactions, we can just solve for whatever that other piece is going to be. Okay. And then with the next one here, using the standard reduction potentials from table 20.1, calculate the standard cell potential for the voltaic cell described by the reaction below. So with it, I just took the two reactions that we'd be looking at there, and have given you this. So this should not be cell here. This should be reduction, and there should be 2 electrons there actually. So with this one, just note that it's not complete because it should also have the 2 electrons on the left-hand side, and it should say reduction here rather than cell, because that's just the reduction half reaction. But see if you can take that information. The number is still going to be correct, but again, we should just have 2 electrons there, and it should really be the cell potential for just the reduction. It should be the reduction potential, really. But see if you can kind of go through and similarly determine what the cell potential for the voltaic cell would be in this case. So we've got both of the pieces. We just want to identify which one is going to be our reaction at the anode, which is going to be the reaction at the cathode, and just figure out how we're going to plug those in. But with this one, if we look at the reaction itself, again, chromium, we've already kind of seen this one, +6 to +3. So this is going to be our reduction piece. That's going to be at the cathode. So we will have 1.33 minus 0.54, because this will be at the anode. So again, I do minus, and then just whatever that number is. You could also just do positive and then negate the number. You're going to wind up with the same thing. But in this case, we should see we're going to get a cell potential, or standard cell potential at least, of 0.79 volts. And again, it's just because we're looking at the reduction potential at the cathode minus the reduction potential at the anode, or plus the oxidation potential at the anode, depending on how you want to think about it. So then this one is a little bit of a different idea. In this case, we've got 2 different half reactions for reduction. And we want to think about if we were to hook this up. So if we were to make a voltaic cell involving these half reactions, what reaction are we going to see at the cathode? What reaction are we going to see at the anode? And then also just what is the overall cell potential going to be there? So with this, just note that the positive cell potential is going to be spontaneous. So we want to think about which one of these do we need to occur at the cathode, which one do we need to occur at the anode in order for the cell potential overall to be positive. And that'll be the way we can determine what substance is being oxidized, what's being reduced, what direction are those electrons going to flow. Is it going to go from tin to cadmium, cadmium to tin? So see if you can kind of think through this one before we go over it together. But again, we just want to think about which of these processes do we need to occur as the reduction at the cathode, as the oxidation at the anode, in order to get an overall positive cell potential. But with it, if we just think about these two values, one of them we're going to have to flip because both of these are the reduction piece, so we can't have both of these substances gaining 2 electrons. We need one of them to give up 2, one of them to gain 2. So if we think about it, we're going to have to flip the sign on one of these. And if we flip the sign on the top one, the larger value, that'll give us a positive number overall. So what we're going to see is the tin will be our reduction piece. The cadmium is going to be our oxidation piece. And just in general, we'll see this on the next slide. The more positive that reduction potential is just going to mean that that's going to be the one that does get reduced. So even though both of these values are negative, since negative 0.136 is more positive than negative 0.403, we're going to see that that'll be our reduction piece, which means we'll have to flip this reaction around for the oxidation. So we'll see cadmium's going to lose 2 electrons to produce cadmium 2 plus. And then those 2 electrons are going to flow across the wire. And then the tin in solution, that tin 2 plus, is going to gain those electrons and just become the solid tin there. So if we look at the actual reactions, like I said, with the reduction one, we don't have to change anything about that. That reaction is going to occur just as it was originally listed, but for the oxidation at the anode, we'll need to flip that one, and that's why we flipped the sign of the value here. And then with it, just note, I actually did the oxidation potentials. So we've got positive oxidation potential rather than minus the reduction potential at the anode. But we'll just see the negative 0.136 plus that positive 0.403 gives us a 0.267 volts there. So we've got a positive standard cell potential, which means that this reaction is going to be spontaneous in this direction. So if we look at the cell diagram itself, we'll have the cadmium is going to be our anode, because that's the oxidation piece. So we'll see the electrons, 2 electrons, are going to flow across this wire. So the solid cadmium is then going to dissolve into solution as cadmium 2 plus. And then cadmium's pretty nasty metal. So if this was to actually dissolve into environmental areas, then that could be problematic. But in a voltaic cell, not too much of an issue. And then those electrons going to move to the cathode. So now we've got the extra electrons here, basically going to attract the tin ions, and we're going to see the tin itself is going to start to coat this cathode just with the solid tin. And then with it, we'd also have the salt bridge, so we'd see positive ions move in this direction to balance out the negative electrons. We'd see negative ions move towards the cadmium beaker to balance out the loss of electrons. But with it, we don't have any information about what those ions would specifically be, like we did with the earlier one with potassium and sulfate. Yeah. But as I just mentioned here, the more positive those reduction potentials are, just the stronger they're going to be as oxidizers. So that's why we saw with the tin there, it had a more positive reduction potential. So the tin got reduced, making it an oxidizing agent or an oxidizer. And what we're going to see is just as that value becomes more positive, the strength of that oxidizing agent increases. So the more likely it is to be reduced, the better it's going to be at oxidizing something else. So if we think about fluorine, it's going to be the strongest oxidizing agent. And that makes sense because with fluorine, it's going to be extremely electronegative. So it's going to be good at pulling in those electrons. It's going to be good at taking electrons from something else. So fluorine itself is going to be reduced, making something else have to get oxidized. That's why we're considering fluorine to be an oxidizing agent or an oxidizer. It's causing something to be oxidized. And then similar to the concept with the conjugate acid, conjugate bases, as the strength of one increased, the strength of the other decreased, we're going to see kind of the same thing here, because as the strength of the oxidizing agent increases, its strength as a reducing agent is going to decrease. So if we think about it just going in the opposite direction now, the fluoride ion isn't going to really ever give up 2 electrons to form just the diatomic fluorine, because in that case, it would mean something's taking those electrons from the fluoride ion. But since fluorine's the most electronegative, that's not ever going to happen. But then if we look at the lithium here, very negative reduction potential means it's going to be a very bad oxidizing agent, but that means it's going to be a very good reducing agent. So if we think about the reaction in the opposite direction here, if it's a reducing agent, that means something else is going to be reduced, something else is going to be gaining electrons. And that makes sense why something like lithium would be a strong reducing agent, because lithium wants to give up that single valence electron it has. So with these ones, just as the reduction potential becomes more positive, the better at oxidizing something it's going to be. And then just the reverse, as it becomes negative, the better it's going to be as a reducing agent. Just because the more likely it is to be oxidized itself. So if we look at these substances here, oops, we need the reactions with them. Take a moment to see if you can identify, based on the nitrate, silver, and dichromate ions, the relative strength of these 3 ions as oxidizing agents. And again, with this one, the strength of an oxidizing agent is going to increase with the positivity of the reduction potential. So as it becomes more positive, the oxidizing agent is going to, or strength of oxidizing agent is going to increase. So what we want to do is just look at these reduction potentials, and we'll see that, oops, just as that number becomes more positive, so 1.33 versus 0.96 versus 0.8, we're going to see those are the stronger oxidizing agents with the higher potential. So in this case, we'll see silver with the lowest value is going to be our worst oxidizing agent. Dichromate would be the strongest, and then the nitrate would just be in the middle there. And then when we're looking at a voltaic cell, we can look at the difference between both of those pieces. So again, we're going to have oxidation at the anode, reduction at the cathode, and just the further separated the reduction potentials are for those 2 pieces, just the greater the voltage on that battery is going to be. So if we had something that was very close to one another in terms of their reduction potential, the voltage is going to be low. But as we get them further and further apart, we're going to see the voltage will increase, just as that gap between the 2 reduction potential increases as well. And then with this, just note, it is just going to be the difference between them. So if we had 0.34 versus negative 0.76, that difference would still be 1.1. That's the same idea if we just had 0 and 1.1 itself. So we're just looking at the difference between those 2. So looking at the table here, see if you can determine the standard cell potential for both of these. And then using the value that you calculate, see if you can determine if that reaction would be spontaneous or not. So with this one, we want to kind of just look to see, based on the reactions we have, what are each of those half reactions going to look like? The reduction one we'll be able to find exactly like it is in this table. The oxidation half reaction will have to flip when we're looking here, just so we can, or we'll have to just think about it going right to left in that case. But we can look to see where those reactions are, look to see what the potential for each of those half reactions are, and then just use the equation to determine the overall cell potential. And then we'll just do that for each of them. And then remember, a positive cell potential represents a spontaneous reaction, a negative cell potential would just be non-spontaneous. So if we look at the ones here, we can see hydrogen is getting reduced, and that's just going to be our reference. So that one's going to be 0. That's going to be our cathode. So with the anode, we're thinking about copper to copper 2 plus. So we're going to have 0.34, but it's going to be 0 minus 0.34. So we'll wind up with a negative 0.34 voltage there. So it's not going to be spontaneous. And then with the second one, we can kind of do the same thing. In this case, chlorine is getting reduced. So we can see one of the better oxidizing agents, we have it really high up on this table, 0.136 volts for the reduction half potential there, reduction potential. And then with the iodide, again, we want to kind of just think about this one in reverse, because in this case, it's getting oxidized. It's going from -1 up to 0. So that's why we're going to have minus the 0.54. But since we've got the larger chlorine value initially, we still wind up with a positive number. So we're going to see in this case that voltaic cell, the reaction would occur spontaneously. And if we think back to the previous chapter with spontaneity, we looked at Gibbs free energy, so delta G, and we saw that a process that had a negative delta G is going to be spontaneous. And then we just talked about how a positive standard cell potential is going to represent spontaneity. So we can kind of see both of those two pieces here, why they make sense, because the relationship between them is just going to be free energy is equal, or the change in free energy is going to be equal to the negative number of moles of electrons transferred times the Faraday constant, which is just the value at the bottom. So 96,485 joules per volt mole. And then E is just going to be the cell potential itself. So if we think about it, if we've got a positive E value here, F is just a constant, always going to be positive. N is just a number. It's always going to be positive. We're not going to have a negative number of moles of electrons transferred. So both of these values are always going to be positive. If E is positive, 3 positives times each other. But we've got the negative sign out front. So that would make this entire term negative. So we'll see that the reason E and negative delta G are both going to represent spontaneity can be kind of derived from this equation. We kind of see that a relationship. If we had a negative cell potential, negative times the negative here would make a positive delta G, so it would just be non-spontaneous in that case. So we can again kind of just see the relationship between the signs of these terms and the reason why we'll have the spontaneity with a positive delta or positive E and a negative delta G. And then with it, we can kind of just take this equation and then just put the degree sign there, just representing standard conditions. So what we want to do here is determine, using this equation, we want to determine what the Gibbs free energy change is going to be for this reaction. So what we need to do first is determine the standard cell potential. We need to look at this reaction, identify what the half reactions are, identify what the cell potential is ultimately going to be. And then we can think about how many electrons are going to be transferred. We can just multiply that by Faraday's constant, switch the signs, so we got the negative sign there, to get the delta G value. And then with the K, we'll just want to think back to the Gibbs free energy equation. So we had delta G is equal to the delta G standard plus RT ln Q. But at equilibrium, delta G on the left is equal to 0. So we can kind of just rearrange that. Q becomes K. But we'll take it one step at a time. And first, we'll just look at getting delta G. And again, like I said, first we need to get the cell potential. So when we're looking at this reaction, I think the silver one is fairly easy to see. We have Ag, and it goes to Ag plus. So we're looking at the reaction here. In this case, the reaction of interest, we're going to see that this is silver getting oxidized. So this will be kind of the second piece of our cell potential equation. And then with the reduction piece, now we're looking at oxygen and hydrogen ions going to water. So we're looking at the very top one here. So when we're looking at calculating delta E, we'll have 1.23 minus 0.8. So we'll get a delta, or we'll get a cell potential of 0.43. And then what we can do is just use that equation we just looked at, multiply it by the number of electrons transferred. In this case, it's going to be 4. So if we look, the first reaction at the top, 4 electrons. The silver one only has 1. but that's why we multiplied it by 4 in the reaction itself, because we need the same number of electrons overall involved. But just recognize this is going to be an intensive property. So when we multiply the number of electrons here, or multiply the reaction itself to get the same number of electrons, that's not going to change the cell potential themselves. So we still have just 0.8 here. We don't have to multiply that by 4 or anything. Where we do use the 4, though, is just in this delta G equation itself. So we've got -4 electrons times the Faraday constant. So you don't need to memorize this number on a quiz or a test. I'll always provide it for you. I don't think it's useful to have that memorized. And then the cell potential itself, so 0.43. And what we're going to see there is, in this case, the standard free energy change is going to be equal to negative 170,000 joules per mole, or negative 170 kilojoules per mole. So both of these values, of course, agree in terms of whether it's going to be spontaneous or not. And then with the second piece, we want to also get the equilibrium constant. So what we have to do is just, again, think back to our previous chapter. We've got delta G is equal to RT ln K. And the reason we have this equation is because normally we would have a plus sign between these two terms, and then just regular delta G on the opposite side. But at equilibrium, that's going to be equal to 0. So we can just rearrange this. Okay. And then just note this should be negative RT. That's how we get rid of the negative sign here. But we should have delta G, our standard free energy change, is equal to negative RT ln K. But when we have the values here, we can just take that delta G we just solved for, plug it in on the left. Again, it should be negative, and then the R value, so 8.314 joules per mole Kelvin, multiply by 298 for the standard temperature, and then we just have ln K. That's what we're looking for here. So the way we got ln K is equal to 69 is just by multiplying these two together and then dividing the free energy change by that value. So we have negative 170,000 divided by 8.314 divided by 298. And that gives us 69, and then we're still just left with ln K. So we can use E to get rid of the natural log, and then we see the equilibrium constant itself is just going to be equal to 9.3 times 10 to the 29th. So we're going to see this reaction. It's going to be a product favor reaction by quite a bit. So we're going to push this reaction very far to the right-hand side. And then this equation is the one that we were just looking at. But again, at equilibrium, delta G on the left is just equal to 0. So we can subtract RT ln Q. And that's why it should be a negative side. We have to subtract it from both sides. And then at equilibrium, Q is just equal to K. That's why we're actually able to solve for it in the previous one. But if delta G is equal to the number of moles or negative number of moles times Faraday constant times the cell potential, we can take that and just plug it back into this equation. And then we have it on both sides. It's just with the degree sign for whether it's the standard conditions or not. But the terms themselves are pretty much the same. And then with it, we can then continue to kind of just rearrange it. So if we go back here, we can take negative NF. So we can take the negative moles of electrons times the Faraday constant and divide everything by it. So we'll just be left with E is equal to the cell potential plus RT ln Q, which we'll have over the negative NF. And that's what we see here. But then we can also just put it in terms of the logarithm rather than the natural log. So it's just where the 2.303 comes from. But they're essentially the same equation there. And then just a little bit more arranging, because if we think about it, R and F are both going to be constants themselves. And if we're thinking about just a specific temperature, if we're thinking about the standard temperature, 298 Kelvin, we can essentially just take all of these terms and just make them an actual number rather than just representing them with the different variables, different symbols rather, because R and F aren't actually variables. And we just get 0.0592. So we can just then basically substitute all of that in for that term there and just get a slightly different form of this equation. But all of those are looking at the same equations, just kind of from a different step in terms of how many of those constants are we actually symbolizing versus just representing with a number here. But now if we look at it, the cell potential, the cell potential is going to be equal to the standard cell potential minus 0.0592 times or divided by the number of electrons transferred times the logarithm of Q. And with this, what that equation implies is that there's going to be some potential for any cell, even if we have the same substance as the electrode, as long as the concentrations aren't equal. Because if we go back here, even if the standard cell potential is 0, as long as Q isn't equal to 1, so as long as log 1 doesn't give us 0, then we'll have some value for this term, making the potential under those conditions non-zero. And the only way Q won't be equal to 1 is just if we've got different concentrations there. So if we think about the potential here, you can see on the right-hand side, we've got 0.5 molar of the nickel solution in both cases. So if we think about Q, it'll be 0.5 over 0.5. Doesn't really matter, products or reactants. But it would just be 0.5 over 0.5. Just giving us 1, so the log of 1 is 0. Anything times 0, so 0.592 doesn't matter how many electrons there are. Anything times 0 is just 0. So that term becomes 0. This was already 0, so there's just no potential in that cell. But if we've got different concentrations here, now we've got a smaller concentration on the left, larger concentration on the right. That's why we can see the difference in the colors of those beakers. We've just got a higher concentration, a deeper, richer color there. So what we're going to see is the electrons in that case actually will flow, just because in that case, Q value isn't going to be equal to 1. So the logarithm as a whole isn't going to be equal to 0. We'll get some value for E there. And then also, I just want to point out, with these voltaic cells, I think all of the ones we've looked at so far have gone left to right. So we've had the anode on the left, the cathode on the right. And that's a pretty standard sort of format for these ones. At least the way I kind of learned it was anode, bridge, cathode. So you can kind of think about A, B, C, just in that order. But you don't necessarily need to. So if we ever had a reaction, if we ever had a diagram like this on a quiz or a test, don't automatically assume that the anode's on the left, the cathode's on the right, because we could as easily just drawn this backwards and kind of just thinking about it, looking at from the other side of the lab bench. So we would still want to, for that particular question, look at the reactions, look to see what's being oxidized, what's being reduced, look to see where we have those substances, just so we can see what direction those electrons are actually going to flow, because it's not always going to be left to right. All right, so if we look at the question here, we want to determine the cell potential for this reaction under non-standard conditions. So again, standard conditions mean concentrations of 1 molar for everything. And we've got that for the hydrogen and the iodide, but the dichromate we've got at 2, the chromium ion we've got at 1 times 10 to the negative 5th molar. So for this one, we've actually seen this reaction already. So we've got the standard cell potential, 0.79 volts. This is one that we looked at earlier in this video, so I'm not going to go through that process again. But the way we got this was just identifying that chromium going from +6 to +3 is the reduction piece. So we can look at our reduction half potentials and see that had a value of 1.33 volts. Do the opposite for the iodine, it's getting oxidized, -1 to 0. Had a reduction half potential of 0.54, so that's why we're going to subtract it here and just get an overall cell potential of 0.79 volts. And then we've got this equation here. So we can think about what we have to plug in. We're going to take 0.79. We'll plug it in as the standard cell potential. With N, that's going to be the number of electrons. And if we think about it, in this case, it's going +6 to +3. So it's losing 3 electrons, or it's gaining 3 electrons, excuse me. But we've got 2 of these chromiums. So we really have 6 electrons involved there. And that's going to be the same thing with the iodide, going from -1 to 0. But we've got 6 of those iodides. So we're going to have 6 electrons involved there. So N is going to be equal to 6 here. And then with Q, we want to think about the equilibrium expression. And in this case, it's going to be, it won't actually be too difficult just because hydrogen and iodide are both equal to 1. So it doesn't really matter that we've got really crazy exponents here. But we just want to make sure that we're representing Q correctly. So it's going to be products over reactants, but it's only going to focus on solutions or gases. So we can ignore the solid iodide, we can ignore the liquid water. And then with these, again, we just want to make sure that we include the coefficients. So for the chromium on top, because we've got products over reactants, we'll square that one. For hydrogen, we'll raise it to the 14th power, iodide to the 6th. But again, for this one, since they're both equal to 1, doesn't really matter at all because it's just still going to be 1 for each of them. But for this reaction, if we plug in the different concentrations into this equation, for Q, what we're going to get is 5.0 times 10 to the -11th. So that's just taking the 1 times 10 to the -5th and squaring it on top, and then doing 2 times 1 to the 14th times 1 to the 6th. That's where I got the 5 times 10 to the -11th here. But if we just go through and then take all those values, plug them in, 0.79 volts minus 0.0592 over 6 times the log of 5 times 10 to the -11, what we're going to see in that case is the cell potential under these conditions are going to be a little bit higher. Instead of 0.79, it's going to be 0.89 volts.